suppose you take the Hodge-Durand kernel is it's like the integral of e to the minus b star b. So it's the inverse of the Laplacian. Whereas b star times the integral of the heat kernel is b star times the Laplacian inverse. And if you think about it, this looks more like inverse of. So this is the inverse of d.
I see, because the kinematics of our system was given by d instead of
exactly.
I mean, instead of the Laplacian in this case.
So if you with d gives an isomorphism from d star to md as an inverse. Inverse is given by that. That's because anytime you have a first order theory. Okay, so what? So last time, we were talking about how does the OR2 flow and the BV formalism fit together. We do this for Chern-Simons theory. We defined delta of L to be contraction with K of L, and we, as we just said, we have this propagator. T, which satisfies the homotopy between the heat kernels at different values of L. And the main result is that if I of epsilon satisfies the scale epsilon quantum master equation, so that takes the form d I of epsilon plus the term, there's a self loop. Oh, thanks. Sorry, it's been invisible, wasn't it? So if this guy satisfies the scale epsilon quantum master equation, then we apply the OR2 flow, we get something satisfying the scale L quantum master equation. So this thing was defined by some kind of a sum over connected graphs. Where I have I epsilon as my vertex, E epsilon L as my propagator. So just like we had right at the beginning. Okay, does everybody reasonably happy with why this was true? Like behind this.
Oh, I had a question about the history.
Yeah?
So Owen's told me that I think that this is your sort of idea, like this particular.
I am not sure I was the first one to make this observation. I mean, there was related results, like if you have some odd symplectic vector space, and then you choose a Lagrangian in some high energy piece, then you can do a partial integration to get an effective solution to the master equation on low energy. So I think Ivan Losev, Andre Losev had a paper about that at some stage in the late 90s.
So, implicit in, say, Singerstein and others' proof of renormalizability using medium non-real presumably also lies a statement of this kind, right?
I am not exactly sure where they would place the quantum master equation. They wouldn't use this language. I found that stuff completely impenetrable. So
Yeah, I mean, it's just, I think they call this the Singerstein equation. They call the quantum master equation the Singerstein equation, and then it was sort of invented back then to try to address this issue. But I mean, again, it's very different proof language. It is where it gets complicated. It's force quantum law, complex.
yeah, I mean, like the statement that the effect of Lagrangian satisfies the quantum master equation is going to be like this will appear in all kinds of ways because it'll appear in like word identities for the BRST operator plays nicely with the OPE. That's also implied by this. So kind of. I think any formalism for quantizing gauge theory will have something equivalent to this. They might use a different language. Okay, so you can ask, how general is this? Like the way we've set it up. So what do we need to be able to do this? All we need is that we take the space of fields including the antifields and so on. This is the linearized BRST operator, which is the de Rham operator for Chern-Simons. And we need a local interaction which satisfies classical master equation. So this, of course, this is something we'll always have. But the particular way we're doing gauge fixing requires a little more, which is not obvious how to get in some situations. We also need Q star, or I sometimes call this kind of gauge fixing operator. This may or may not be the adjoint of this guy. Sometimes it is, sometimes it isn't. That's not very important. And this must satisfy square to 0, that the commutator, it must satisfy the formal properties we're familiar with for quantum mechanics, for the de Rham operator, which is basically the same as the formal properties some people might be familiar with for n equals 2 quantum mechanics, over space of n equals 2 quantum mechanics. Commutator of Q and Q star must be equal to what's called a generalized Laplacian. Delta. So this is, if you give me any operator, who knows if you can write down the heat kernel for it? But there's a criterion that if it looks like the Laplacian, then it has a nice heat kernel. So generalized Laplacian means it looks like the Laplacian times the identity matrix plus order less than or equal to 1 operators. That's all it means. The order reciprocal 1 operators can be anything, any order 1, any order 0. It's just the order 2 part has to be the usual Laplacian for some metric. Now, so you can ask, does Yang-Mills theories have this kind of feature? And at a first glance, the answer is no. So you have to work a bit to put it into this form. So then the space of fields looks like in degree -1, it's 0 forms. In degree 0, it's 1 forms. And then in degree 1, it's 3 forms for a 4 manifold. In degree 2, it's 4 forms. And the linearized BRST operator, it has a funny term here in the middle. So this part is the usual de Rham operator, just because that's how gauge transformations work. But the part going from 1 to 3 forms is a bit funny, because this is the part that imposes the Yang-Mills equation. The Yang-Mills equation is a second order equation. So the linearized Yang-Mills equation tells us that a 1 form is in the kernel of B star D. So because this piece here is second order, so if we took the adjoint Q star to Q, then this will also be of second order. So this commutator will be of order 4. And that's bad. So you don't want to do that. So you kind of have to think a bit, like in the way we're setting things up. Maybe in other ways of doing field theory, you can treat things directly like this, but the way we're doing it, you have to work a little bit to fix this problem. So the solution is to put it in the first order formulation. So here the fundamental fields are A, so 1 form, and a 4 manifold, and B, which is a self-dual 2 form. So, and then the Lagrangian is integral B wedge FA plus Yang-Mills coupling constant times integral trace B squared. Okay. So this Lagrangian is in fact completely equivalent to the standard Yang-Mills Lagrangian. The reason being the field B, the kinetic term of the field B is no derivatives. So the field B, it doesn't really propagate. Its propagator is a delta. So we can integrate out the field B without destroying any locality, because propagator is a delta function. If we integrate out B, we don't spread things out on the domain. The traditional way of seeing how that works is if you perform a change of coordinates, something like B. Let's stop this code. if you do this change of coordinates, then this term gets cancelled. We get 1 over 4 integral f a plus wedge f a plus integral b squared, because the cross terms cancel. And fa plus is the self-dual part. So this is 1 over 4 integral 1 plus star f a wedge 1 plus star f a. So if you calculate this a bit further, this is the Yang-Mills action plus a topological term. F wedge star f plus integral f. So up to some constants, we get this whole thing is equivalent to Yang-Mills action plus a topological term plus this field b squared, this field b, the quadratic Lagrangian b squared, which does not interact with any of the other fields. Okay, any questions about this?
Do you have to shift b by fa plus to make sure it stays so?
Yes, thank you.
So the copying for the topological term presumably would be absorbed in that factor.
Yes. Yeah, I mean, I can always add on a topological term in this first order formulation, but here, like, there's a particular, this Lagrangian will be Yang-Mills with a particular value of the theta angle of the topological term. So if we do this,
Sorry, could you just say, was it supposed to be obvious here why this first term has F pluses in both? I mean, you started with B wedge F.
here,
Yeah, how did that F turn into an F plus?
well, if B is self-dual, then B with F minus is 0.
Oh, right, sorry. Yep.
Any other questions? So if we put it in this first order form, then we find that the linearized BRST operator that has this nicer form. It looks much more like a Dram operator. So in degree -1, we have the gauge symmetry as usual. In degree 0, we have our fields A and B. And because the kinetic term includes EDA, we're going to have a term like this, where this 3 form is the antifield of this 1 form. We're also going to have a term like that. That's just the Dram operator. And the B squared term will contribute something going like that. That's going to be G Yang-Mills times the identity. So it looks like 2 copies of truncated Dram complex, where the differential is first order, and it's much nicer. But with this cross term given of order 0, proportional to the Yang-Mills couple. So now I think we're in a much better situation. To gauge fix, we just use D star. We define the gauge fixing operator, D star, and then Q, E, well, so Q D star will be E D star plus Well, this cross term is not quite D, so it'll give you something else, plus an order 1 operator. So that's much nicer. This is the Laplacian plus an order 1 operator. So this is fine. Yeah.
So for the gauge fixing operator, we just have like horizontal arrows going backwards and no diagonal.
Yeah. Exactly, yeah. Actually, an alternative way to do this, so that if you do that, then, I mean, because of this order 1 term, the propagator will not be like a block diagonal matrix. It'll have off-diagonal terms from the,
Straight down.
yeah, exactly. So it'll be some kind of triangular matrix. So an alternative way to work, which is like also like totally fine, is to that you can absorb this trace b squared term into the interaction. And treat it as a vertex. So if you do that, then your propagator doesn't have this kind of funny off-diagonal piece, but we have this bivalent vertex with the factor of G Young-Mills. Yep. Yeah.
So usually you don't allow quadratic vertices because like
The infinite sums.
yeah,
Yeah, but if you, we're going to put a small parameter next to it.
so
The Young-Mills cup.
there's a form you can take the form properties of G and H bar.
Yeah, although you don't, you can, if you do it like this, I think you only need, you can set H bar equals 1, because this is small. Okay, so this may be a little technical, but either way works, and you can analyze the theory this way.
Is the star of a sweeper always self?
What's that?
Is the star of a sweeper always self?
I should be more precise. I meant the projection of the star onto the sun.
So the same thing as taking the form of adjoint.
Yes, it is. Yeah. So yeah, there's certainly a formula for like these stars, like star D star. There's going to be some formula for projection and something. Any other questions? Would it help to write down the propagator explicitly? Yeah. Okay. I'll see if I can manage it. So the propagator is going to be like D star Laplacian inverse. So first we're going to write down the formula for this guy. So Laplacian inverse as a kernel, which is one of R squared So we take this form and we do a projection onto So we do a projection onto forms where in the x variables it's in omega 2 plus, omega 3, omega 4, and the y variables it's in omega 0, omega 1, omega 2 plus. Okay. Make sense? So what am I writing down, just to be clear? So this, what I'm writing down, is the integral from 0 to infinity of the heat kernel, where kT is defined in the setting where we treat the trace b squared as a vertex. Yes, exactly. Otherwise, there would be a term where which the propagator connected this truncation with itself. So, for example, now if we now to write down the propagator, we should apply d star to this. D star, which is some d by dxi, contract with xi. And this will give us xi minus yi over x minus y to the fourth. It'll give us something of this form, but where we project or where we do some projection onto the forms of the right degrees. So from this, I think we can calculate the term in the propagator of Gauss number 0 really explicitly. Let's say the y is a 1 form and x is a subtotal 2 form. There should be something like, say, dy1 over x minus y to the fourth times x2 minus y2 dx3 3 dx4 plus dx1 dx2 plus permutations. I think this is the form the propagator will take. Yeah.
Might have said this, but what form would be of that if we can think the mode would be different? As in if it didn't.
Right. So we have to think about like the Q is like D plus some identity operator, D star. So the thing we're going to think about is this identity operator, the anti-commutator of that with that. So this. So this will have a term where I do, this is this identity operator, where I go from there to there by D star. And it will have another term where I go from there to there by D star. And what will happen is the heat kernel is going to look like, so I view the heat kernel as an operator instead of a kernel. It looks like the exponential minus T ED star, this is the usual thing, plus minus T ID ED star. And this term commutes to this operator, and it also squares to 0. So I can just bring it down. It's something like 1 minus T times so it'll be a sum of two terms, one of which is the usual heat kernel, and one of which looks like the star of the heat kernel going from here to here.
Thank you.
Okay, I'm not sure I got this 100% correct, but like I hope we got it sufficiently close that you guys could, if you really wanted to sit down and work out the propagator, you could use what we said to figure it out, the first order Yang moles. So what I wanted to say was, so now we have some feeling for how we can put first order Yang mills into this setting, and probably the easiest thing to do it will be to use the B-square term as a vertex. And so this is totally fine. And actually it's equivalent because it'll be this term will be that vertex, like that. Vertex propagator will be that term. So what I wanted to say is to say a little bit about how to, what does it mean to have an interacting theory in the BB formalism and how to construct it. Yeah?
So up here we were on R4, right?
Yeah.
So are we taking the heat kernel with certain decay, the decay condition from the fields and kernel?
Yeah, so that's kind of, I mean, there's like a standard heat kernel for flat space. And that's characterized by its exponential decay. Yeah. It's also characterized by its symmetries. It's, has all the symmetries.
So in that case, is the kernel not unique, but equals the symmetries of which decay condition?
Yes. we want it to be, I'm trying to remember this. Yeah, if you had some manifold, which, some random non-compact manifold, then you absolutely have to impose the decay conditions. But if you're in flat space, it would be strange not to use the standard heat kernel, because I think it's the only one with this translation variant, if I remember correctly. Okay, so what does it mean to have an interacting theory in the BV formalism? So given some space of fields, as above, if we want to choose a gauge fixing condition, so we want to have a collection functionals I have L, which satisfy the orgy flow equation. So we must also want them to satisfy the same things we did before. I of L is local. So if you remember from like the beginning, what this is a bit subtle because at the quantum level, I of L gets poles in L as it gets smaller. But what you want is that if two of the fields I insert have disjoint support, then it should decay rapidly. Well, mod H bar, I must recover my classical Lagrangian. But the classical Lagrangian should be the L to 0 limit, mod H bar. But so this is all what we had, if we didn't have the BV formalism, this is what we had. But the additional ingredient is that we want the quantum master equation satisfied. So this guy will satisfy the scale L quantum master equation. So how would we construct something like this? Well, without the quantum master equation, everything is exactly as it was before. You could just say, well, I choose some scheme, a way of extracting the singular parts of my functions, and then I construct these guys by sticking in a Lagrangian and subtracting up the singular parts. So without the quantum master equation, the set of such IL is in bijection with series in H bar whose coefficients are Lagrangians. And so how that works, you take a series in H bar whose coefficients are Lagrangians, and then you say, well, you choose some scheme that tells me what counterterms I need to do to make the whole thing finite and produce this. But now we're left with a rather difficult problem of checking, given a series in H bar, these coefficients are Lagrangians, does the resulting thing satisfy the quantum master equation? Now, if you were to try to calculate this explicitly, the quantum master equation looks like, naively, it's quadratic plus linear in your Lagrangian. But this effective quantum master equation is not. Yes. So the effective Lagrangian is a complicated function of this series. It's a function of all polynomial degrees. So the effective quantum master equation is a very complicated equation on this side. So in practice, if you're faced with this kind of problem, you can never actually check explicitly whether or not the effective quantum master equation holds, except at one loop in practice, unless you're some kind of calculational wizard and maybe you could do two loops. But I literally only know computations at one loop, such as the Green-Schwarz computation. So the way you would actually do this is by cohomological methods. So the way this works is, suppose we have some I of L and we know by induction that it satisfies the quantum master equation up to some order. And then the theorem is that we let the obstruction the coefficient. So the obstruction is going to be the coefficient of HR to the n in the failure of this to satisfy the quantum master equation. So this quantity, the advantage is modulo h bar to the n, so we pick up its leading term. That's the obstruction to satisfying the quantum master equation in the next order. And then this obstruction will have a bunch of nice properties which will allow us to analyze if we can go one more order in H. So the properties are firstly, I take here I0, I mean the h bar to the 0 term. Plus epsilon OL. This is epsilon is an odd parameter. This guy satisfies the classical a mod h bar orgy flow. it also satisfies this classical master equation. So the important thing is that everything about the obstruction will be related to the classical Lagrangian. And here we have I0 classical Lagrangian. So a lift of I to a solution to the quantum master equation modulo h bar to the n plus 1 is the same as finding some, I'll call it J, which satisfies 1 and okay. So this satisfies the classical orgy flow, classical master, in this case classical master equation, and solution to the quantum master equation to the next order is making this guy exact in this cochain. Any questions about this? I'm not sure I'm going to have time to go through the proof. I mean, well, maybe rather than going through the proof, this is a kind of universal phenomenon in mathematics. If I'm deforming some object, then the obstruction, deforming it to the nth order, is a deformation of the classical things. It's always true. I mean, it's just one of the things of deformation theory, deformation obstruction theory.
Sure, so this would be how you would establish whether something is an allowed counter term at order h bar power n, provided you know the counter terms to order h bar power n as well.
Well, yeah. So suppose you know the counter terms of order h modulo h bar to the n, which satisfies the quantum master equation, and those counter terms you've chosen may fail to satisfy the quantum master equation of the next order.
Right.
And we have to choose a counter term which makes the quantum master equation hold. So this quantity here is like, this is the problem caused by the counter terms you've already chosen. And here, can I find a counter term in the next order which fixes that problem? So maybe the most useful form of this statement is that when I send, because this satisfies the classical version of the orgy flow involving trees, you can show that its L to 0 limit exists. So alternative, or better formulation, the L to 0 limit exists. Call it O, and then the classical Lagrangian 0 and a lift to a solution to the quantum master equation modulo h bar to the n plus 1 is equal to finding some j, where qj plus ij equal to L. So everything is controlled by the cohomology of this complex. So So let's say it a bit more formally. So we let OL be the complex of local functionals with differential Q plus I. So this is, so a degree 0 element of here will be a term I can add to the Lagrangian. Degree 0 element will be closed if it's a consistent deformation of my tensor Lagrangian. And what these arguments, which we've kind of sketched, tell us is that the obstruction can be viewed as a cohomology class in H1, the space of local functionals. And if the obstruction is equal to 0, there exists a lift to a solution to the quantum master equation to the next order. And the set of lifts is parameterized by H0. Okay, so that
why is the likelihood 0 and not O?
this here? Well, it's saying if the cohomology class is 0. Oh yeah, sorry. Oh. Too many similar symbols.
Is it very similar to anomalies?
Yeah, this is anomalies. Yeah.
So if you wanted to classify anomalies for some particular low symmetry or something like that?
Well, yeah, that would be related. These are gauge anomalies. So if you wanted to have anomalies for some global symmetries, the way you might do it is you would introduce some background fields and have a similar complex, which is a function of your physical fields and your background fields. So in the physics literature, they talk about terms in that complex which depend, they're polynomials of different order in the different fields and call them mixed anomalies. It's not really actually meaningful to break it up like that because the differential mixes everything up. But yeah.
So the statement that you just did the classical RG flow equation to analyze this, is it similar to what we usually call the Renormalization consistency conditions in where we usually study tangent anomalies? Because there you're...
So I think the Weissman conditions are that the anomaly is closed.
Right.
So, so the statement that the limit exists is like, a priori the anomaly at some scale is a non-local thing, but if all previous anomalies vanish, then actually it can be, like the first non-zero anomaly can be made local. And then this equation is the Weissman condition.
The lifts sort of have an equivalence condition on them that I never.
Why is it H0 and not?
Yeah, like the immediate, like what I see is C0, like how you get the lifts parameterized by C0, but then there's like some extra relation you have to take into account.
Right. So in general, like if I add on a term to my Lagrangian, which can be absorbed by a change of coordinates in the fields, then it's to be viewed as trivial. So the equivalence relation is those things I can add on modulo those which can be absorbed by change of coordinates.
This could be like a non-linear change of coordinates.
Yes, a nonlinear change of coordinates. But we're doing it the first order. That's 1 plus epsilon, something nonlinear.
So where does you see this class H1 is measuring whether you can lift to the next order, but what does next order mean? Like the n disappeared from this side of the board.
Right. Well, you know, if H1 vanishes, then we can always lift every order. If H1 doesn't vanish, then at each order in n, I'll find a class. And if that class is non-zero, then I stop there. Like I
You mean that this O is naturally a power series at each bar, and that you get one of these classes.
No, I wouldn't say that. I'd say like once you've say killed the first obstruction at order h bar to the 1, then the next obstruction is defined.
O will also be some class.
Well, some class in the same thing. So there, yeah.
There's like, I mean, it's not a power series, but it does depend on the order in H bar.
Exactly.
So the OC has
So if you prove that this H1 is 0, then you're done.
Yes. But then you might think, well, H0 might be right. Or maybe H1 is 0 only if you impose certain symmetries. So at this point, there's a bit of an art to figuring out what happens. Symmetries, scaling symmetries. Okay, any other questions? Do you guys want me to explain why any of these equations hold, or is it going to be just... Yeah? Okay, so... Well, anybody who doesn't want can head off, I suppose. Oh, and by the way, I'm happy to meet next week if people are around. Are you guys around next week? Well, are you here? Are you? You are? Okay. Yeah, so let's continue next week. So why do these equations hold? So let's write out diagrammatically the formula for the obstruction. So it's U applied to IN of L plus some plus so because it's at order n, so this is the order n term in the solution to the quantum mass equation, or in the quantum mass equation. So let's check the first thing, like why does this satisfy the classical master equation? And we'll see like a bunch of terms cancel. So what is, we want to check that Q of OL plus OL KL I0 L is equal to 0. So we apply Q. So the first term, of course, is going to vanish because Q squared is 0. Now is the point I have to think a little bit. So we know what Q of I OR is as long as OR is less than N. Because I OR of L OR is less than N is this kind of thing. Because we know that it satisfies the quantum master equation up to order N. So there's a term here, which is in this sum, it's like a problematic term, which we can bring to the other side. We're going to mess around, the signs are going to be a bit messed up. Minus and that's looking good because that's part of, that's the thing we wanted with the sign error. And now we're going to split these up further. It's something like this. Yeah.
So the second to last diagram you drew, is that coming both from both of the two terms?
Yes.
Above?
Yeah, exactly. It's coming from both of them. So let's think a little bit. So what we want to say is that everything on the right-hand side cancels because everything appears twice, except for some terms which have an I0 stuck off. So here, everything appears twice, except, well, I've already removed the one with the I0. So the I0 ones only appear once. Opposite signs, except the terms with an I0. Yeah, they only appear once. I mean, like, so, like this guy, it can appear, but I mean, it was a bit sloppy. This Q can go here, or it can go here. This term can appear from expanding this one or from expanding this one. Opposite signs. This one can appear from expanding here or expanding here. And this one can appear from expanding here, but there's some kind of symmetry. Yeah, this. If I flip these two legs, I pick up a sign because these are odd. Whereas this whole thing is totally symmetric on all of its inputs. So that is 2. But the only, if you think about it, the only ones that don't appear twice are the ones with the I0. And that is exactly what we want. So we get I0 and 0. Okay. So there's a more algebraic proof in my book. So might ask what. So now you can also check, and I think in a kind of the same way, if we add h bar to the n j of L to I of L, then the obstruction, this is actually easier, is satisfying the quantum master equation, is now, well, let's just calculate it. I'd order h bar to the n. Well, we have what we had before. Plus, and let's think of what terms can this contribute to the quantum master. It can't contribute any things with the self edge, because that has a vertex of order n minus 1. So the only things it can contribute are this. Plus so this tells us if we can find that OL is of this form, then the obstruction can be. So the other features, why does this satisfy the classical orgy flow? I'm not sure I want to go through all of that right now, but the way it will work is you differentiate this with respect to L, and you look on the other side. So you differentiate this with respect to L, and you look on the other side. Well, I know all of these satisfy the orgy flow equation, infinitesimal orgy flow equation. So I know what their L derivatives are. I also know what the L derivatives of these guys are. And you write down everything, and everything cancels except for a term involving an edge coming off with an I0. So by a kind of similar kind of fiddling around. And again, there's a more algebraic argument. Anything else? Any other questions? So maybe next time we can calculate some cohomology groups.